When we capture an event through different perceptual channels, like audio waveforms and dense visual pixel grids, we are attempting to integrate data structures that lack a common physical basis. This collision of formats is the starting point for multimodal learning. This is the core challenge of multimodal representation learning. These data channels are physically asymmetric, differing in their native resolution, their spatial coverage, and their noise characteristics. Because of these differences, a paired multimodal sample rarely maps perfectly one-to-one between the two streams. Instead, every sample contains a unique combination of overlapping semantic data, paired with modality-unique information that exists in only one of the two channels. Biological brains handle this integration seamlessly, but learning algorithms do not. They must be explicitly engineered to determine what to align, retain, and discard. To manage this integration, the current industry paradigm relies on a single strategy: collapsing heterogeneous data into a uniform mathematical space. This approach creates what is known as a monolithic latent embedding. To map data into this space, engineers generally use one of two dominant training methods: contrastive learning or infomax. Mathematically, both monolithic approaches fail when dealing with modality-unique cues. They break down in complementary ways, leaving Bayes' optimal performance out of reach. Achieving a mathematically optimal, minimal sufficient statistic requires us to abandon the monolithic embedding entirely. We need a structural, routed architecture, a system known as the S3 framework. To understand exactly where these architectures fail, we have to view multimodal data through the parameters of a strict latent factor model. This diagram represents the physical decomposition of a multimodal input. It splits into one shared factor and two distinct modality-unique factors. The shared factor, x sub s, represents the direct semantic overlap. The unique factors, x sub 1u and x sub 2u, represent specific nuances appearing in only one perceptual channel. To predict a downstream task variable y, the model requires a combination of both shared and unique factors for high accuracy. The mathematical ideal for a model is to satisfy the equality condition of the data processing inequality. An optimal representation must act as a completely sufficient statistic for task y. This ensures zero task-relevant data is lost during encoding. Let's test multimodal contrastive learning against that ideal. This method focuses entirely on cross-modal alignment. This equation represents the contrastive objective. When we map it onto our latent factor model, it illuminates only the shared pathway. Because it maximizes mutual information across paired modalities, the result depends solely on the entropy of the shared factor. According to Proposition 2.5, this representation fails whenever the downstream task relies on modality-unique information. It creates a shared-only bias, where the active alignment actively suppresses task-relevant unique signals. Contrastive learning structurally guarantees the loss of unique data, inherently violating the requirement for task sufficiency. Infomax-style methods attempt to recover the unique signals discarded by contrastive objectives by preserving all information within the monolithic embedding. As the infomax objective maps onto our variables, it captures the shared and unique factors, but the latent space becomes saturated with visual static. By maximizing total information, the model simultaneously maximizes task-irrelevant information. It retains the signal, but it also captures all the noise. This violates Poole's info-min principle, which states that representations must be minimal with respect to the input to be effective. Infomax creates a latent space completely saturated with variables that have no predictive value, which severely degrades downstream predictability. Escaping this trade-off requires us to decompose the embedding space into interpretable semantic units. This is the logic behind the S3 framework: specialization, selection, and sparsification. The system is driven by a dynamic routing mechanism that handles the selection phase of the framework. We replace the monolithic block with a field of concept-level experts. This handles the specialization phase. By distributing alignment across these distinct semantic subspaces, the model mitigates the asymmetry of the original modalities. Based on the task demands, the router dynamically activates only the experts needed for that specific goal. This mechanism strips away the task-irrelevant noise that plagues traditional Infomax approaches. Sparsification successfully achieves information minimality, leaving an information-dense representation behind. Empirical testing across multi-bench benchmarks confirms that this structural theory holds consistently. When we map sparsity against accuracy, we see a distinct reverse U-shaped trend. Performance peaks at an intermediate optimal level of sparsity. At this point, essential signals are preserved while noise is suppressed. This peak sits between two suboptimal extremes, the data loss of high sparsity and the noisy claw of low sparsity. The mixture of experts architecture provides the structural basis for semantic interpretability, serving as more than a mechanism for parameter scaling. Structuring multimodal models as selectable semantic components is the most principled, mathematically grounded path towards representations that are truly task-sufficient and information minimal.